All right. So today, what I want to talk about is repeated measures designs. These are very common. You're going to find if you go to the thesis conference, which is just in a few weeks, or even the thesis poster presentation. I encourage you to go to that too on Friday the 14th. I don't know exactly where yet, but go just to see what your colleagues, your student colleagues, are working on. And you'll see a lot of repeated measures. You're going to see a lot of people testing people more than once, which is all a repeated measures design is. So, let's say you're interested in learning or forgetting, which, again, a lot of what we do is about learning and forgetting. When you think about anything about memory is always about learning and forgetting. Without this kind of design, I wouldn't have all the letters after my name. Because, learning, you have to test the same subjects over and over again, right? So independent groups won't do here. I can't really have a group that has no trials, a group with one trial, a group with two trials, a group with three trials. It just doesn't work like that, right? So you're going to want to test people over and over again. The same people, the same chickadees, whatever the hell you're testing, you want to test them more than once to see the change over time, to see what's called a learning curve, right? By the way, a steep learning curve means the task is easy. I know the world doesn't talk like that, and to communicate with other people, you're going to have to make this stupid mistake too of saying a steep learning curve means it's hard. But think about this for a second. If you go from 0 to 100, really in one trial, oh, it's a really steep learning curve, but you've learned everything in one trial. Oh, a gradual learning curve, very slowly, would mean it's harder, wouldn't it? You don't walk up the damn curve. Oh, it's harder to get up the curve. It means it's actually easier. You're not walking on a freaking graph. Anyway, it's one of those things that the way the public talks about things and the way experts talk is different. That happens a lot, and it's really annoying sometimes being an expert in something. You'll hear experimental psychologists always say, actually that means it's easy. It drives all of us nuts, and we just let it go. But I thought I'd mention it here. All right. So you can test the same people or whomever, whatever it is, pigeons, chickadees, rats, whatever, over and over again, and look at change over time. Right? That's what learning would be, right? It's just change over time. Okay. I mean, it's a little more complicated than that, obviously. But we'll look at change over time. All right. So you get something like this. If we have 3 retention intervals for a memory test, 5 minutes, 1 hour, and 24 hours, that's a common enough one. We have the same group in all 3. It's the same people tested. 5-minute retention interval, 1 hour retention interval, 24-hour retention interval. And we've given them 20 words to study. Okay, so I give all you guys 20 words to study, and then 5 minutes later, I ask you to repeat the words, and then 1 hour later I ask you, and then 24 hours later I ask you. And we all know what we get. You get a nice declining curve. You get a forgetting curve. Right? First discovered by Ebbinghaus, right? The little curve in Ebbinghaus. So the design's actually really simple. These kind of designs are pretty simple. They're very powerful. You probably, I hope, have detected a potential problem with this. The observations aren't independent anymore. And I'm always saying, no, you gotta have independence of observations. You can't repeat. If I know Chloe's score, I don't know Andy's score, right? I can't, they're independent, except that if I'm testing Chloe over and over again, if I know Chloe's score from 5 minutes, I can make a pretty good guess at 1 hour, and a pretty good guess at 24 hours, because I know how she is at 5 minutes. Oh, in fact, the scores aren't literally dependent on each other. They're dependent on you being you, you being you, and you being you. That's not good. Let's just put it in the modeling. So what we'll do is we'll mathematically model this. We're just going to throw this in the model for analysis of variance, and everything will be fine. Okay, yeah, let's do that. So, the model looks like this. X equals nu plus tau plus pi plus epsilon. That's any score equals the grand mean plus any treatment effect. So so far this just looks like straight ahead analysis of variance. An error you know about. So x equals mu plus tau plus epsilon is we're ignoring the pi for a second here, is the model for a straight ahead one-way analysis of variance. We've just added something new in here, and that's the effect of subjects. Pi standing for people here. I don't know if that's what it stands for, but it always, to me, makes it easy to remember. Okay. So all we've done here is say, okay, we've got these effects, and also let's just put into the fact that we have all these individuals that are different from each other. Their scores are dependent on each other. So we just brought it into the model. You got to remember, of course, that this kind of dependence is incredibly special. We still don't know Andy's score if we know Chloe's score. But if we know Chloe's score, we can make some other guesses at Chloe's other scores. The model can, basically. So we still don't have, we still have independence of each observation from each person. So within each person, I'm sorry, I should back up. Within each person, the scores depend on each other, but between people, the scores don't depend on each other. Because you're still all different people. Okay. Does that make sense so far? Questions? Yeah, please.
How did you say the last sentence once again?
Yeah, so if we know, the scores are dependent on each other, but only within each person. So if we're testing Reese 5 times in a row, we get 1, 2, 3, 4, 5, and that's all just Reese's scores. Okay, but then we compare Reese's scores to Skylar's scores. They're independent of each other. But all Skylar's scores are dependent on each other themselves because they're all his. Right? So there's the difference there. That we still have independence of sets of observations, basically. So if I know your scores, I don't know your scores. I can't. But if I know your score for 5 minutes, it's probably, then we look at 1 hour and 24 hours, well, clearly they're dependent on each other because it's you and the variable here, pi, it's the level of you. Okay? Does that make sense?
Yes.
Cool. Okay. Sometimes I'm surprised when I'm able to explain things, which is sad, really, because I should be pretty confident in my ability at this point. All right. Okay. So design, what we're going to do is here, I'm going to make a design that looks like this. We're going to have now 4 people, subjects 1, 2, 3, and 4. And we have 5 minutes, 1 hour, 24 hours. That's our retention intervals. And group 1, and group, it's just we have one group, is subjects 1 to 4. So the question you're always asking yourself is, we've decreased error. Well, the first thing you're always thinking rather is you've decreased error. You must have. Because think about this. Okay, so it's x equals mu plus tau plus pi plus epsilon. And the model for just straight ahead analysis of variance is x equals mu plus tau. Why did I put a cross in it? Plus epsilon. Well, let's see, this is here, this is here. Oh, it must be making error smaller because we're splitting error up into something a little bit more. We're splitting it up into now 2 things, error and the effect of subjects. So we've made error get smaller. Error getting smaller is good. It makes, because think about this. F equals tau plus epsilon over epsilon. If we're making the bottom of the fraction smaller, we're making the f test bigger. And the bigger the f, the easier it is to find a significant difference. So what we have then is more statistical power. Usually, because we actually lost degrees of freedom. And the lower your degrees of freedom, the larger the critical value of f. If you just look at f, you'll see that the smaller numbers have higher f values you have to exceed. Okay. Okay. So what I'm showing you, well, let's look at this. It would look like this. The analysis, I'm not showing any mean squares or anything, but the differences look like this. If we did this with a one-way ANOVA, you can analyze those data with a one-way ANOVA. It's a mistake because you're losing statistical power, but you can do it. Again, the numbers don't know where they come from. And it looks like this. Retention interval has 2 degrees of freedom. Remember, we had 3 retention intervals. Total of 12 observations, so 11 degrees of freedom, so we have 9 for error. Oh, here, look, we have error has 6. If we do the repeated measures, we have an effective subject that has 3 degrees of freedom. Retention interval still has 2, and the total has 11. And in fact, your next assignment, right, assignment 3, one of the questions is, was it worth doing this? So you'll see this, you'll end up having to do these kind of things. All right. I really don't feel well. Okay. So any design has a finite amount of variation and a finite number of degrees of freedom. Okay. So we've partitioned the degrees of freedom and the variation a little bit further. That's all we've done by adding in the p-hole effect, adding in the pi. Okay, that's all we've done there, is we've partitioned the degrees of freedom and the variation just a little bit more, making the error term smaller, and that's almost always going to be good. Mean squared for retention interval, by the way, will be the same for both analyses. If you just go back and look at that previous slide, you'll see that the number of degrees of freedom for retention interval would be the same. It's 2 for both of them. Oh, jeez, I feel so shitty. Okay. All right. So the question you're always asking is the reduction in mean squared error worth the loss of degrees of freedom for error? Again, look at any F table. The larger the degrees of freedom, the smaller the F. So therefore, the smaller the degrees of freedom, the larger the F that you have to exceed the critical value. You're always trying to get that error to be small. Okay? And it's almost always worth it. Okay. All right. Questions so far? Okay. So let's think about this a bit. I've given you kind of an idealized version of the world, but is it realistic to think this would happen? X equals mu plus tau plus pi plus epsilon. Shouldn't tau interact with pi? Think about this. Again, our retention interval experiment. And maybe my curve looks like, my forgetting curve looks like this. And maybe your forgetting curve looks like this. And maybe yours looks like this. And maybe yours looks more like that. Oh, so you're saying that each subject has a different, the effective retention interval changes depending upon the subject. Yeah, it's an interaction. It's an interaction between subjects, individuals, and whatever the variable is in our case here, the retention interval. And that actually sounds like the way the world does work. So we should probably change our model. In fact, it's pretty sensible to assume it does. Like there's individual differences. Even in fundamental cognitive processes like forgetting, there are individual differences, and everybody's a little bit different, and the effect of the treatment will change depending upon the person. Okay? All right. So our model's going to change. Our new model is x equals mu plus tau plus pi plus tau pi. That's our new model. X equals mu plus tau plus pi plus tau pi. It is there, and you might say, where's the error? Well, there isn't an error term there. Well, there is an error term, but there's not one we're going to call epsilon. Because we've used up all the degrees of freedom. We've accounted for everything. So we don't have anything left over that we just call error. We've exhausted the degrees of freedom. There aren't any more. So what we've done here is we've treated S subjects as just some other variable. Because they are. You're all just, like each of you as individuals are different subjects and have different levels of whatever it is you have. So really you are a variable. So in fact, the weird thing is here, this retention interval by subject has the same number of degrees of freedom as the old error term. It's actually even calculated the same way. We're just giving it a different name, okay? But there's nothing that says error. There's nothing there that says mean squared error. What are we going to divide by? Right, because we have to divide mean squared for treatment, or retention interval in this case we'll call it, divided by something, and there's no thing there that says error. And we've always been looking for something that says error. We don't have anything. How the hell is this going to work? The error term is actually a treatment by subject interaction. So we end up using the interaction, the tau pi interaction, the treatment by subject interaction. We end up using that as our error term. So we divide mean squared for retention interval by mean squared for retention interval by subject. So subjects are a random factor. Oh, this is why I talked about random factors the other day in fixed factors. Subjects are a random factor. They're way closer to a random factor than a fixed factor. When I talk about forgetting, and if I do a forgetting experiment, I'm not just talking about forgetting in you guys. I'm talking about forgetting in people. I'm thinking of you guys as being kind of a stand-in for a random sample of humans. I'm not just interested in how it affects you, I'm interested in how it affects all of the humans. So therefore, we can think of subjects as a random factor. This is why I talked about random effects and fixed effects the other day. When you might have been wondering, why is he explaining this to us if he said that we never do this? Because this is how the error term ends up working. We don't test the subject factor. So there's also mean squared for subjects. There's no error term for it. And we don't test it. Like, we don't do an F-test. And you might say, but why? Because here's the earth-shattering thing you'd find if you could actually do a test of subjects. That's that people are different from each other. Ooh, Nobel Prize time. We all knew that already, right? We all knew that we were all different from each other. Look at us, we're all just different. So if that's the case, that would be nothing. It wouldn't be interesting if we could test it, and we can't anyway. There's no error term, there's no mean square with an expected value that we can divide by. So it doesn't matter, we just leave it there. It's something we've removed. The point of repeated measures is we've removed variation because we're testing the same people over and over again. Okay? Can't test mean squared subjects. There's no error term with the correct expected value. And who cares? The nice thing about this is, and who cares? Because if this mattered, we'd be like scratching our heads going, oh, we still have to test this, but we don't. Because it's not interesting that Vera is different from Chloe. That's not an interesting piece of data. You're not getting a publication that's saying, two women in their 20s are different from each other. Like, that's not a paper. You're not getting tenure with that. Like, you're not going to grad school with that. That's not a discovery. Look, they're different. That was easy. Next. So, who cares that we can't test it? The nice thing is, at first you think, oh, we should find out. But what if we did? Oh, boy, you found out people are different from each other. We didn't go Einstein. So, it's not interesting anyway. So, it doesn't matter. Okay, questions about that before we move on to what I've talked about here is the repeated measures is a special case of something more general called a randomized block design. You might say, why are you talking about that then after? Because I think it's easier to understand the special case before you understand the general, which is weird, but it's, I think, true. But any questions so far on this repeated measure stuff? And a lot of us use these designs all the time because we test animals over and over again. We test people over and over again. It's the thing. You're looking at change over time. You're looking at learning or forgetting. You have to test people over and over again. Okay. Questions though, you're good? Everybody's okay? All right. Okay, so let's talk about the more general case, which is called the randomized block design. So remember we talked about the matched pairs or correlated t-test. That's the one where if instead of it's the same formula as doing repeated measures t-test, before and after kind of thing. But what we do is we match subjects up. So let's pretend that you guys are very similar on something. We'll match you guys up, then we'll match you guys up. And we consider you as, with the t-test, as basically one observation. What we're going to do here is we're going to consider, let's say we're going to make sure that all all five of you in the front row here are, let's pretend that you're all very similar in something. And what I've done here is I've said I'm going to block on a variable, whatever this variable is. So that's the general case. The specific case we just talked about is the ultimate version of something you block on. It's the same person. But you're not all the same people. But I've measured something about you that's important. Right, so like I said, before and after or whatever, look for subjects, effects. Subjects usually match an independent variable. So let's say it was a blood pressure drug I was testing. And I tested and found that you guys all had exactly the same blood pressure, so I put you guys in a group. Or a block, is what I call it. Okay? I've got what I think is a pretty good example coming up. Okay. So, what we're going to do is we're going to do analysis of variance on these blocks of subjects. We're just extending the logic of a t-test that has repeated measures, or has correlated measures. What we need in this case is a weird assumption called homogeneity of experimental units. Subjects are experimental units. So that says that within each block, you should be the same on some variable. Homogeneous, the same. Okay? And you're going to get this because you wouldn't block on something where people weren't all the same. And again, I'll show you in a second what I mean. And I think I got a pretty good example. So this can be achieved in a few ways. We could use litter mates, which you guys clearly aren't all related. Looking at you. You're not litter mates. Also, you're all roughly the same age, so that would have been a hell of a time for your collective mother. Matched pairs, twins, things like that. Or we just match on a variable. Okay. So here, this is called blocking. And this is, the thing we block on is called a nuisance variable. It's a variable we can measure and remove the variance, but it isn't important to us. It's a nuisance. It's a problem. So that's called a nuisance variable. Okay? This is going to reduce error, which is going to give us more power. And that's what we want. And our structural model is going to be very similar to what we saw from repeated measures. It's almost exactly the same. But it's more like the one. Yeah, so let's show you the model. All right, x equals, it's the same one from repeated measures when we started, and I said, you can't do that. There should be an interaction. Well, not with blocks, we wouldn't do that. So this is any score equals the grand mean plus a treatment effect, and then the block you're in. And then finally, of course, error or residual. So I'm going to explain this with, I think, a pretty cool example in just a sec. But we've got to get some things out of the way first. All right. The questions so far, do you see the place we would use this? And I think, again, with the example, you'll see situations where we would use this approach. Okay. So first of all, a few assumptions. Pi, that's the effect of blocks, is normal and independent with a mean of 0 and a variance of sigma squared sub pi. And the same thing with error, normally distributed, independent, mean of zero, variance of sigma squared sub epsilon. These are just the things we would normally expect. Error is independent of block. So that means what's left over doesn't change depending upon the block you're in. That's an important thing. Also, there's no interactions between tau and pi. Remember I said with repeated measures, with the same person tested over and over again, it makes sense to say there's an interaction of tau and pi. We can't really do that when we have individuals in a block. So there can't be an interaction between tau and pi. Well, what if we do if there is an interaction? Well, then error goes up, because the only place that look at the model, x equals mu, here it is here, x equals mu plus tau plus pi plus epsilon. If there's some interaction between, I don't know, tau and pi or pi and epsilon, the only place that can go is the error. It's the only place it can go, so it's going to make error bigger. Big error bad. Small error good. Because we're dividing by error, we want big F number. We want a big F in number. Okay? So if you actually do have that interaction, you're going to lose power if you have an interaction between blocks and groups. So again, I have a pretty nice example coming up here that should tie it all together. Yeah, that's the next slide. So basically, so how do you deal with having interactions between blocks and groups? Don't. That's how. And then you might say, well, Dave, that's not very satisfactory. Too bad. That's what you do. Don't have that interaction. So let me explain with an example what we're talking about here, because I think it helps. So let's say we have 3 methods of studying. Let's go with learning a language. Let's say learning French. Most of us in here are Anglophones. So learning French in school. And there's going to be 3 methods. There's going to be method 1, method 2, method 3, and method 1 is, I don't know, straight up lecture like I'm doing here. Method 2 is going to be, more stupid pedagogical garbage. I don't know, active learning. So something where you do a lot of exercises and crap, I don't know. Oh, we'll make the final one. So regular, yeah, let's do that. So this is regular lecture. This is sort of more active learning approach. And this one might be sort of immersion. Let's go with that. Okay. But you might think that, like, you start learning French in Ontario in school in, depending where you live, at grade 3. Depending where you live. There's 500,000 Franco-Ontarians. Some people in this province speak French as their mother tongue. I think they're going to be different from people who did French immersion, from people who just did regular core French in school. So it makes sense for us to put them in different blocks. So we'll put all the people who are Franco-Ontarians, people who actually speak French as their mother tongue, we're going to put them in one block. Because they will probably be affected by learning methods of French differently than people who just had core French or people who went to French immersion. Makes sense, doesn't it? So what we have here are we got low, medium, and high. That's just experience with French is what I'm using there. Okay? So low is just regular core French. This will be immersion, and the top one here, high experience. That's somebody who grew up speaking French. So you see what we're doing here is we're basically just putting 3 of each in a block. Because your former or your previous knowledge of the language should affect how you learn the language, how you do on a language test. We want to remove that effect. So let's just put people in blocks and take that effect out. Does that make sense? It looks like it does. I see I see some nods. Remember, I'm so full of stimulants right now, it may just be the world's moving. So, okay. When you take like cold medicine like that, you feel okay, but you know in the background, I don't feel okay. That's the thing. So like, I can function right now, but I don't feel well. I am not good. Anyway, do you see why we're doing this? Does this make sense? And the ultimate version of this would be the same person tested 3 times. That's the special case. The general case is we just have different people. Okay? So you can see why this would be an important thing to do, and we can deal with this nicely. But the problem we have is, what do we do if there's an interaction? Well, we actually have an interaction here, don't we? Because those lines are parallel. So we actually have a block by treatment interaction, which we're not supposed to have. Look, the lines don't cross, we should just be happy. You're going to get some interaction probably, you just don't want a whole lot. The nice thing is having the interaction will make your statistical test more conservative, so you're not going to make a fool of yourself, you just might miss something that's there. Okay. So that's the logic of this. Now let's put these things together. Oh, I've got 2 repeated measures besides here. Repeated measures variables, I'm sorry. So I'm going to give you a list of words, 20 words, and then at 5 minutes, 1 hour, and 24 hours, I'm going to give you 2 different memory tests. I'm going to give you an explicit test, which is I'm going to say, please recall the words that I presented to you. And then I'm going to give you what's called an implicit test. And what I'll use is word fragment completion. So if one of the words you saw was, on the list of words was chickadee, I would have you fill in this. Okay, so that's chickadee, you have to fill in the blanks. You will do that better for the word chickadee than you would do it for a word that you hadn't seen. Priming of implicit memory using word fragment completion. Take memory next year, learn all about it. Now, the cool thing about this kind of task is it doesn't decay. So if you did 5 minutes, 1 hour, 24 hours, and you saw the explicit part, tell me the words, that decays nicely. Nice forgetting curve. The implicit task is straight. There are 2 different memory systems. The cool thing is, you may not even remember that you saw the word chickadee, but you will fill it in better than a word you hadn't seen before. But you may not even be aware of it. People with amnesia show completely normal priming of implicit memory. Very cool. Very cool. What's going to happen in this experiment is you're going to get implicit's going to be a straight line. This is going to be a regular forgetting curve. We're looking for an interaction between memory test type and retention interval, which you would get, by the way. This is, don't make this your honors thesis. Tolving, Schachter, and Stark, 1982, already did this. Okay, so pretty famous paper. Okay, what's the model? Okay, soon we're going to stop worrying about the model because they start to get so complicated and not useful. But let's just, there's the model, x equals mu plus alpha plus beta plus, okay, so far this looks normal because we have 2 independent variables. Then we got to worry about the subjects, plus pi, plus alpha pi, plus beta pi, plus alpha beta pi, which sounds like some fraternity in some stupid movie from the 1980s. I'm so glad we don't have fraternities. They're just stupid. I'm going to go out on a limb and say it's stupid. Anyway. think we live in the States. Not anymore, I hope we don't. Right. There's a lot of terms here, and a lot of error terms, potential error terms. Look at all these things with pi in them, because those are going to be the error terms, right? How do we know what to test with what? Right? We have to know what mean squared to divide by what other mean squared. We got to know what the mean squared errors are, and there's going to be different error terms for different tests. Now, there's a few ways you can do this. If you are incredibly mathematically inclined, you could work out the expected values of the mean squares. No one here wants to do that. Nice smile. I didn't saw that from here. You could do that, but no one does that. Because there's an algorithm you can use that works every single time. An algorithm is a thing that always finds the correct solution, and a heuristic is something that gets you to the correct solution. So there's an algorithm I'm going to teach you, and it's really quite basic and simple. It's called Yates order. It's named after Frank Yates, the guy who we talked about Yates before. And he figured this out. So it works like this. The first thing we do is we list our subjects. Oh, I said we had 10 subjects, so let's not even worry about the degrees of freedom yet. The next thing we're going to say is retention interval. Remember, it was 5 minutes, 1 hour, 24 hours. And now we go subjects by retention interval. And then we go memory test type. I'm going to call that M. And now I go M by S, M by Ri, M by S by Ri, done. Subjects, and then each individual variable. Now, how do I know what to test with what? Well, we don't test subjects. As I said, you don't, because who cares that we find out that individuals are different from each other? That's not a result. Well, it's a result, it's just not an interesting one. But if I'm going to divide mean squared for retention interval by mean squared for subjects by retention interval. I'm going to divide mean squared for memory test type by mean squared for memory test type times subjects. I'm going to divide mean squared for memory times retention interval by the three-way interaction. So for any design, I can figure this out. You might think, well, why does this matter? Shouldn't the computer do it automatically? Well, no. If we don't have the repeated measures pack, we don't need it. We don't need it because in SPSS, all we would do is just tell it that, oh, subjects are a random variable, a random factor, and the other two are fixed factors, and it would figure it out. But PSPP, if you're using it, doesn't do that. So when you do PSPP, you put all the values in it, you're going to get a whole bunch of things saying it can't figure out the numbers. So it'll give you the mean squares, it can't do the F-tests. What you have to do in that case is get out a calculator and actually divide one mean square by another to do the F-tests yourselves by hand. But you get all the mean squares, it's not hard. There is a video I've posted, I don't know if I put this in the LMS, I know it's on my YouTube channel, about how to do assignment 3 with PSPP. If it's not posted in the LMS, I'll do that later. This is going to become a thing that we do, is I give you a design, and believe me, it's way more complicated than this. This just has two repeated measures, factors. I could go 2 repeated and 1 independent. Like, think about this. All the work I did for all my PhD stuff was comparing 2 species, that's independent groups. But I was testing their memory, so that's going to be repeated measures because I'm trying to see how well they learn over time. And then there's different kinds of things I was testing them on, memory for space and color. So I had 2 repeated variables and 1 independent variable. So I can think of, this one be, I don't know, experiment like 7 in my PhD thesis is a 2 by 2 by 60 bins? Yeah, I think 60. Analysis of variance, 2 between, 1 within. Sorry, 1 between, 2 within. So we do this all the time. It's very common that we mix and match these designs. All right. Repeated measures used lots in psychology because we're interested in change over time. It's just, forgetting and remembering and learning, obviously, is about change over time. And the biggest thing you have to do here, and once you get this in your head, you'll be fine. You're treating subjects like they're any other factor. They're just some other variable. They're a variable that we are going to assume is a random factor. This now allows us to figure out error terms. Like I said, if you want to do the deriving the expected values of the mean squares and doing it from first principles, go nuts. I don't know how to do that. I know people who do know how to do it. I just don't know how. I can do it without a book in front of me. I got a friend who has a math degree. Her undergrad's in math, and her PhD's in psychology. And when we were in grad school, we would give each other old stats tests. Because, we all do that, right? Old tests float around, you use them to study. And I remember I saw one of hers, Chris Hitchcock, and she's very bright. Chris is very smart, and she's a mathematician. And she didn't do this. She actually just worked out the expected values of the mean squares by hand because she could. And it's funny because she gave us photocopies of her tests to use to study. And Ian, the Scottish guy I told you about, wrote on it as a comment, "Don't you think this is a bit much?" Which I think is pretty great. But she did it right. But you know what? You don't have to do that. You learn this very simple algorithm, and it always gets you the right answer. It's a matter of practicing these things. And oh boy, are we going to practice them. So finding out error terms and components of a model like this, and listing all these things is called Yates order, and putting them in Yates order. It's something that, typically if you Google this, you won't even find anything. Like, I don't think people call it that. It's something that my old stats prof called Yates order, and he said it's done in the order that he would present things in, but it's not something that's, you hear a lot about. But what Yates order is it's just a series, it's a series of rules that allows you to find expected values of mean squares into partition degrees of freedom. And as we go along, you're going to hear a lot more about it. Questions about this stuff today? Okay. You sure you got nothing? You sure? You just all want to go home. So do I. Get out of here. What class got canceled?